It's a great honor to be given this opportunity to present at the method lecture. So I'll be talking about empirical-based method. This is a topic very close to my heart, and I would like to share with everyone here today. So here you see a picture of Roger Conker, so with whom I have a long-standing collaboration on this topic. We have had a very fun journey working through this. I remember that we went to the library of the Columbia University looking through the archive of Herbert Robbins. It was great fun to find a lot of treasure there. So I encourage everyone, if you had a chance, to try it out there. And I'm extremely grateful to have Roger as my advisor, who introduced me to the wonderful empirical-based world. So here is how the outline gonna look like. So I'll be starting off with some motivating examples with teacher value added, and show how it has a connection to the so-called compound decision problem that is as a terminology used in the stats literature. Then I will give much detail on the so-called normal mean problem and introduce what everybody probably is familiar with on the parametric shrinkage method, as well as the non-parametric shrinkage method, which probably is not as well known, but is very powerful for large-scale estimation and inference problem. Then I'll be talking about computation methods, which really unlocks the possibility of going towards these non-parametric techniques. Then I'll deviate from the normal mean problem and talk about other compound decisions that has connections to multiple testing, ranking, and selections. I'll end with empirical-based inference, which is relatively underdeveloped, that hopefully today's talk gonna inspire more research in this area. If time permits, I'll go beyond normal models and talk about mixture models in general. Okay, so let me start off with this motivating example. It's probably simplified away from a lot of complications, but would help us to get what's the key object that we have in mind. So let the Yij tilde be denoted as the test outcomes of student J taught by teacher I. Right? So in the literature of education economics, we typically run this so-called value-added regression, where the covariates Xij captures a rich collection of information on student family background, lag test scores, teacher characteristics, and all that. And also the alpha I is the so-called value-added of teacher I. In the classical panel data literature, this would be nothing but the teacher fixed effects. Our goal, and that will be the focus of today's lecture, is trying to estimate the whole vector of alpha 1 to alpha n. Now, we might be interested in this because either we want a systematic way of evaluating teachers, or we might be interested to know what is the heterogeneity of the teacher quality, or there might be policy that requires us to select top or bottom quality teachers. So all of that involves estimation of these fixed effects. We would start off our analysis with the familiar fixed effects estimator for alpha I, which is nothing but the teacher-specific sample mean once you purge away the effects of the covariates. And Ji here denotes the number of students teacher I has taught. Okay, when Ji is reasonably large, then it's reasonable to assume that we have a normal model on the teacher-specific sample mean, with the location as the teacher quality, alpha I, and here the variance would depend on how many students this teacher has taught. Now, naturally, in this application, we will be facing the complication of variance heterogeneity. In the beginning of my lecture, I would abstract away from that, and then I'll bring it back, just to kind of bring out some key intuitions. Okay, so what is a key feature of this estimation problem, right? So essentially, it can be summarized that we are facing an independent statistical decision problem. We observe some data which leads to Yi, and our goal is to estimate alpha I for all the individual teachers. Now, this n independent problem has common structure in the sense that given an alpha I, they are all having the same model. Here I denoted as P. In the teacher context, they are all normally distributed with the location parameter being alpha I. And n, which is the total number of simultaneous problems we are considering, is typically large at least in modern application. And most importantly, we care about collective performance, right? In the sense that we want to come up with estimator for the vector of alpha that has good performance as a whole, like considering n problems simultaneously. So these features put together is precisely what defines a compound decision problem. First, be given the name in the 1951 paper of Herbert Robbins. So to put it in contrast with simple decision problem, right? So here the key feature is that simple decision problem would be ignoring the ensemble of n problems and just be coming up with estimators using individual i's data for individual i's parameter. Whereas the compound decision problem would take into account that we are really estimating n parameters at the same time. Okay, so now there are two types of assumptions that one could consider imposing on the vector alpha. One is the familiar fixed effects model, where these vector alpha are just treated as some unknown parameters. The other, slightly tightened assumption, which is the random effects model, is to consider this vector alpha as a vector of random variable coming from some common distribution G. For instance, alpha i's are just random IID jors from the distribution G. Sometimes the literature reserves the name compound decision to correspond to the fixed effects model and reserve the name empirical base for the random effects model, but that's really just terminologies. Okay, so let's formulate this compound decision problem, right? So we have yi measuring the outcome. We have some model to characterize the randomness of yi given this key parameter of interest alpha I. We would like to estimate all these alpha i's. Now, let's denote the vector of estimators that we could come up with for the vector of alpha as delta, just to sort out some notation. And this delta, of course, would be depending on the vector of data that we observe. Okay? And now, in order to evaluate different estimators, we need to come up with the loss function. So the loss function, because we are considering n problems simultaneously, naturally has this sample average kind of form where we are just adding up losses for each individual estimation and divided by how many problems we are considered as a whole. Now, zooming in, there are different type of loss function one could consider. The most commonly used is the squared error loss, where we just are taking the usual Euclidean distance. We could also consider other form. For instance, the absolute error loss is also used in the literature. What is risk? Okay, risk is nothing but expected loss, right? So in our context, a priori, individual estimator for alpha I could potentially depend on the entire vector of y. So therefore, when we write out the expectation, it's with respect to this product measure of all these n DGPs. Now, the key of the compound decision problem is estimation risk of each individual matters. However, they are being aggregated. So that's going to matter a lot for estimators that I'm going to introduce forward. So let's zoom in to the so-called normal mean problem, right? So let's specialize the distribution P to be normal. And here I have simplified the variance to be the same across individuals. So this is the homogeneous variance assumption, which is strong, right? But I will relax that later. And let's use the commonly used squared error loss. For that, our goal is to come up with estimator that try to make the compound risk small. Okay? There are two well-known estimators. The first, of course, is the maximum likelihood estimator, also called the fixed effect estimator. So the fixed effect estimator is only using information from individual I, which is kind of a priori natural because all these n problems are independent. Why would I want to use other people's information to estimate my own alpha I? However, there is also this I believe well-known linear shrinkage estimator, first proposed by James and Stein in 1961, which basically is a shrinkage estimator, right? So we are putting a shrinkage factor in front of each individual yi. And this shrinkage factor is going to be depending on the entire data, y1 to yn. So in the sense that what James Stein is proposing is a data-dependent shrinkage for each individual coordinates problem. And there is this very powerful result in Stein 1956, as well as in the James and Stein paper in 1961, which shows that the maximum likelihood estimator is inadmissible in the sense that the risk of using MLE is going to be dominated by the James Stein estimator as soon as sample size n is greater than or equals to 3, and for any vector of alpha. So this is a very powerful finite sample frequentist result. Now let's try to understand where does it come from. So first of all, why are we doing shrinkage, right? So think about the extreme case where suppose all the alpha i's are 0, then the yi are really just noise. Then to shrink them makes a lot of sense, right? Because you want to get rid of those noise and coming up with a better estimate for the vector of alpha. But the key catch is they come up with an estimator that dominates in any situations and for any vector of alpha. How does that go? So now let's consider the class of linear shrinkage estimator. So here I have specialized my estimator delta to just be a shrinkage estimator for a shrinkage factor 1 minus b, where b is any fixed constant that is greater than or equals to 0. And note that b equals to 0 would include the maximum likelihood estimator. So we can easily write down what is the compound risk for these class of linear shrinkage estimator. So these will take this form. Now a natural idea is to look for the optimal b that will minimize the compound risk within this class of estimator. So if we do that, we're going to find that the optimal b, denoted as b star here, going to take this form. Now let's take a look at that. So that optimal b going to depends on the entire vector of alpha. So that's not very useful, right? Because I don't know what alpha is, then I wouldn't know what is the b star. But the key observations that James and Stein made is that the b star indeed depends on alpha, but it only depends on alpha through the second moments of the data, yi, right? So in this normal mean model, it's easy to see that the second moments is equals to 1 plus alpha I squared, which is in this summand in the denominator that chip into the optimal shrinkage. So then the idea is basically to come up with sample counterpart, right, that mimics the expectation. So that's why this sum of yi squared terms, and the n minus 2 factor is to adjust for the fact that we are having an inverse instead of just the sum itself, right? So this is in the denominator. So indeed, they then show that with this data-dependent prior, right, now it depends on all the y's, they show that the risk of the James-Stein estimator can be upper bounded by the right-hand side quantity. When all the alpha i's are 0, that's where we see the biggest improvement in terms of risk in comparison to the MLE, is that we have a risk bound of 2 over n instead of 1 for the maximum likelihood estimator. Now, it's also easy to see that as long as n is greater than or equals to 3, we always have an improvement. The idea of the James-Stein estimator is essentially to use shrinkage to introduce some bias to each individual estimator, but to improve the overall performance in terms of the compound risk. Now, later on in the 70s, Efference and Morris, in the 1973 paper, gives a Bayesian interpretation of this frequentist shrinkage. So now let's consider the random effects assumption, where all the alpha i's are IID Jor from some distribution G, and in their context, let's specialize to the normal distribution with 0 mean and variance A. Now with this, we have a Bayesian model, where the G is just a subjective prior on these alpha i's. So in the Bayesian world, a natural optimal principle is then to write down the Bayes risk, which I write here, and to minimize that, which will lead to the Bayes estimator. Okay? And with the squared error loss, that comes back to be the familiar posterior mean. For the normal mean problem, this posterior mean gonna take this linear shrinkage form, where the shrinkage factor gonna depends on the variance of A, which appears in the prior. Now notice that the marginal distribution of y in the normal mean model is this multivariate normal with this variance covariance matrix. So the sum of the square of them is going to follow a scaled chi-square. Then we can find an unbiased estimator for the shrinkage factor, which is exactly the shrinkage factor in James-Stein estimator, n minus 2 divided by the sum of squares. So in essence, the James-Stein estimator basically replaced the unknown shrinkage, right? So here 1 over A plus 1 in the Bayes estimator by an unbiased estimator that comes up from the data. And this gives to the rise the name empirical base, because we are estimating some unknown quantity in the prior. So when the prior is normal, then James-Stein estimator is mimicking the optimal base estimator. But recall, Stein's result holds without any Bayesian assumption on the vector of alpha. Any vector of alpha would have improvement in terms of mean squared error. There are a couple of extensions on the James-Stein estimator. For instance, we note that the shrinkage factor is always strictly positive. So put a positive part on the shrinkage terms would provide some further improvement, especially for small n. We could also generalize the prior G to have an unknown center, alpha 0, right? Then the optimal base estimator gonna shrink the individual yi towards that common prior mean, alpha 0, and the corresponding James-Stein estimator is basically replacing the sample counterpart on the unknown pieces in the prior, in our case here, alpha 0 and A. And it's easy to show that these estimator, again, would dominate the maximum likelihood estimator in terms of compound risk when n is greater than or equals to 4. And there are many other variants that would arise. For instance, heterogeneous variance, how would we work through to get the James-Stein estimator? And I'll refer to those variants in Chris' section. Let's see how much improvement we get by doing this. So this is taken from Efference and Morris, 1975, where we have 18 baseball players. We observe their number of hits out of their first 45 at-bats in the season. So NI here denotes the number of at-bats. What we want to do is to predict for the remainder of the season how their hitting performance would look like. A natural model on the hits would be the binomial with the number of at-bats as the number of trials, as well as the success probability, denoted as PI here, measuring hitting performance. Efference Morris suggested a variance stabilizing transformation, which will bring us back to the normal mean model, right? So once you do this transformation, we approximately have a normal distribution for this transformed quantity, and our goal is to estimate alpha I, which links back to the hitting performance. So for mean squared error comparison, where we use the remaining season's realized outcomes as to calculate the true value of alpha I, we see a big reduction in terms of mean squared error by just using the James-Stein shrinkage. So this could be very, very meaningful empirically. Now, a natural question to ask is there a room for further improvement, right? Recall the intuition that under the fixed effects assumption, James-Stein estimator is trying to mimic the optimal estimator in the class of linear shrinkage estimator. Can we do better if we enlarge this class? Using the random effect assumption or the Bayesian context, James-Stein estimator is mimicking the optimal base estimator when the prior is normal. Then the natural question becomes, what if the prior is not normal? What should we do? So in order to bring that out, let me bring you back to the compound decision problem. And this is really teased out in the early paper of Robbins, the 51 and 56 paper. So let's go back to the fixed effects model, where the vector of alpha is just fixed parameters. Now, let's suppose that yi, given alpha I, has this density denoted as P. So it can be any well-defined density. Let's consider a slightly larger class of estimator, right? So instead of forcing the attention to the linear shrinkage estimator, let's consider some function T that is applied on individual coordinates. So these are the so-called separable estimator. If we are focusing on this class of separable estimator, then the following lines gonna lead to the fundamental theorem of compound decision. So these are very important derivations. I want to go slowly on them. So on the left-hand side, we have the defined compound risk, right? So these are just expectation of the loss. Sorry. Because we are using separable estimator, this allows me to replace my general delta to just be a t function applied on yi. And now because of this, the expectation can be applied on each individual coordinates. That leads to the next line, where I replace the expectation by the integral form with respect to the density, P, for each individual, and integrate it out, right? And the last line here is to notice that because we have a sample average here, And that's nothing but taking another integral with respect to the empirical measure of alpha. Right? So these Gn here are nothing but the empirical CDF of the vector of parameter alpha 1 to alpha n. So what has this brought us? This essentially connects the compound risk to the base risk of a single copy of the compound problem with a very specific prior. So this prior, Gn, makes the link back to the compound risk. Okay, so what's going on is, since we've connected compound risk to base risk with a specific prior, now pretending that we know that prior, we could work out the Bayes rule, which will optimize or minimize the base risk, equivalently minimize the compound risk. Now, but since we don't know Gn, why don't we learn it from the data? So we have y1 to yn containing information about alpha 1 to alpha n. Is there a way to let us estimate this empirical measure, right? So this distribution Gn. And this link, or these results of connecting the compound risk to base risk, holds for any density P and for any loss function. So it's quite generic as a machinery. Now let's think back to the James-Stein estimator, right? It did actually estimate the second moment of that distribution, because that optimal B star thus connects back to the second moment of alpha I. And that's enough if we consider linear shrinkage. Robbins, being more ambitious, would ask us to estimate the whole distribution of Gn, hence giving rise to the name non-parametric empirical base. So we are really trying to learn not just parameters in some prior that are subjective, we're trying to learn the prior as a whole, like this Gn measure. So, and Robbins' estimator is more ambitious than linear shrinkage because it's targeting the minimum of the compound risk, right, because of the connection back to compound risk, as well as he's considering a larger class of estimators. Okay, zooming back into the normal mean model, we have the squared error loss. For any Gn that you pass on to me, then the optimal base estimator is again posterior mean, which would take this form. Okay, so then let's ask the question, is it feasible, right, to estimate this Gn? This sounds like a great plan, but is this implementable? So Gn is unknown. We can estimate it from the data. I'm going to show you an example why this is doable. And the idea is to estimate that and plugging in to get a mimic rule for the optimal base estimator. So this in the literature is called the G modeling because it's trying to target Gn. And it's applicable for any form of the conditional density, right? So normal, Poisson, gamma, anything that we have in the empirical context. And also just to remark, the estimation of G is a deconvolution problem, right? In the normal mean problem here, we observe yi, we know ui is normally distributed. All we want is to back out what's the distribution of alpha I. So this is a classical deconvolution. In the normal mean problem, we have something further specialized, right? So the base estimator in the normal mean, where we replace this P by the Gaussian density, gonna lead to the well-known Tweedy formula. Okay, so let's take a look at the Tweedy formula. So the Tweedy formula says that the posterior mean in the normal mean problem gonna be yi, the original coordinate of the information, plus an additional term that depends on the marginal density of y, right? So here, what f of y is this mixture model. So this is the marginal density of y, as well as its derivative. So this leads to an alternative strategy of proceeding to have a non-parametric estimate for the posterior mean is the so-called F modeling, where why don't we just target on estimating the marginal density? That sounds like a more natural and simpler problem because we have kernel methods and all that. But I just want to point out here at least that this is specific to the Tweedy formula, hence specific to the normal model. But the G modeling would be more generic. And further on later in computation section, I'll comment on what's the drawback of F modeling. So suppose we stick to the idea of G modeling and trying to ambitiously estimate these Gn non-parametrically. Can it backfire, right? Our target is to try to minimize the compound risk. But in the past, we need to non-parametrically estimate some quantity, which can be hard. Can it actually lead to a risk that is substantially inflated? And the good news is we have good theoretical guarantee for non-parametric empirical Bayes estimator. So consider just a plug-in estimator for the posterior mean, which is the optimal Bayes estimator, with the non-parametric maximum likelihood estimator for this probability measure Gn. And let's denote the minimum risk target, which is the minimum of the Bayes risk, which is equivalently the minimum of the compound risk. Jiang and Zhang, 2009, shows that the non-parametric empirical Bayes estimator is asymptotically optimal among all separable estimator. What does it mean? It means that the regret, which is the difference between the risk of using this plugging in non-parametric EB estimator versus the minimum risk target, is going to be proportionally vanishing, right? So this is O1 multiplied by the minimum risk target, uniformly for a wide collection of vector alpha. So this suggests that estimating Gn when we target these optimal Bayes estimators does not incur a huge price. So as sample size goes large, we're doing well. Now, what about variance heterogeneity, right? So recall that I begin off with the teacher value-added example, where inherently we have heterogeneous variance across teachers. Different teachers teach different number of students. There are two ways to proceed to handle this. One is to assume that the number of students each teacher teach is independent to his or her underlying quality. With this assumption, we can proceed similarly to deconvolve and estimate the distribution G of the alpha non-parametrically, just do a deconvolution under a heterogeneous variance Gaussian model. So there are technical results that guarantees that that's identified and behaves well. We could also consider a richer model where we leverage on the panel structure of the teacher context, where each individual teacher I teach multiple students. So this number of students play the role as the time dimension in the classical panel data. And then we could introduce an additional unknown quantity, theta I, as the variance of Uij, and pretend that we don't know about that. And we can proceed to just estimate the joint distribution of both the location, alpha I, as well as the scale parameter, theta I. This is done in the paper with Roger, where we apply this technique to estimating income dynamics using PSID data. And there are some further theoretical literature follow-up along that lines. OK, so now comes the question. We have two tools, parametric shrinkage and non-parametric shrinkage. Which one should we use, right? So in final example, the performance difference between the parametric and the non-parametric method gonna depend on the underlying G, how does the distribution of the vector alpha look like, as well as the sample size. So the non-parametric methods offer an adaptive kind of approach, right? As long as n is reasonably large, then it's not gonna be much worse off if the G is really can be approximately well by a normal distribution. But it can be much better for other shape of G that could be looking very different from the normal distribution. And here I would give a common wisdom kind of comments where if your n is really small, then maybe using parametric method of a more parsimonious estimation problems might be better off in practice. Okay, but the typical assumption that we have in mind, having a large n seems to unlock the benefits of using non-parametric methods. So here is just a simulation exercise trying to compare this perspective. So I'm generating data from the normal mean model where there is built-in variance heterogeneity. So J here stands for 8 students or 16 students taught by this teacher I with equal probability. Okay, so this is just a stylized example where I've tried a variety of different sample size starting from 100 all the way stepping up to 12K. So 12K is roughly the size of the applications that we have in mind using these methods. So on the left-hand side figure, where I'm plotting the risk ratio of either the parametric or the non-parametric estimator versus the risk benchmark, where we utilize the infeasible knowledge of the true DGP for G, right? So on the left figure, the true DGP is indeed the G follows a normal distribution. While on the right-hand side, it corresponds to a DGP where we have a mixed of normal. And this mixture of normal has the feature that the majority of the mass is centered around 0, And there are two little piles of mass centered around -1 and 1. And this mixed normal is calibrated so that we have the same mean and variance as the first DGP. So their mean and the variance will be matched exactly to the normal distribution in the first DGP. So the risk ratio here is quite revealing. We can see that if you have a problem as small as just n equals to 100, then you are better off using the parametric method, right? You do pay some price of estimating Gn non-parametrically, but these gonna converge down to the same performance of the parametric as well as the infeasible benchmark, which is 1 here, as sample size march on to be larger. On the right-hand side, the parametric methods, having this risk marked out as red, never improves, right? Because it's stuck with the Gaussian prior, and its estimate for its variance and the mean is just gonna be as good when n is 100 versus n is 12K. Versus the non-parametric methods really march on to the benchmark as sample size goes up. Okay, and let's see where does that gain come from, right? So let me give you some visualization of how shrinkage is done differently between the parametric and non-parametric method in the second DGP. So if the DGP of G is the mixed of normal, on the left-hand side, I'm printing on the y-axis the data, or the maximum likelihood estimator, y, and on the y-axis, the different shrinkage method, right? So the solid black line is how the parametric shrinkage method would work. It's gonna be linear, as a linear function of y. It's gonna shrink, right? So it deviates from the 45-degree line, which is the dashed black line here. The red curve corresponds to the non-parametric shrinkage. Now we see that it's a lot more complicated, right? So for instance, there is a region of y values that it almost does no shrinkage, as well as down below here, whereas there are regions of y values it does more aggressive shrinkage compared to the linear shrinkage method. So on the right-hand side here, I'm just plotting you how for each different values of y for a collection of representative points, how shrinkage is being done. So on the top here, it's as if we pretend that we are always using the normal model as our prior. So here we see all values of y gonna shrink back to the common mean 0. And the further out you are, the more shrinkage you get. That's just a built-in feature of linear shrinkage. For the non-parametric shrinkage, right, so it's a bit smarter, as in values around -1 and 1, those are the two little masses of teachers that we had in that DGP, is not gonna be shrink much. They're gonna stay around there, whereas values further out gonna be shrink less aggressively back to 0, but shrink towards those two centers, right? Which makes a lot of sense because if a teacher is really a good teacher, which belongs to this mass 1, if his outcomes is further out in the tail, why should we penalize it all the way back to 0? So it's all built in automatically in this non-parametric shrinkage method. Okay, so how does it work in real data, right? So all that is simulation. So we did try this method out on the Los Angeles school district data. So these are primary school outcomes, grade 3 and 5, where we have student and teacher matched outcomes. And these rounds out to be about 11K teachers. Controlling for a rich set of covariates, we calculate teacher-specific mean, which then leads to the stylized model that I begin off with. We're gonna compare the difference between using the parametric methods, which is commonly done in this literature, versus how does the non-parametric shrinkage would look like. So first, let me show you what is the estimate for G, right? So that's a G modeling key ingredient which chip into the non-parametric or parametric estimator. So the black line here is where normality is imposed. And the red line here is a non-parametric maximum likelihood estimator for the G. On the vertical dotted line, I mark out the bottom 5% as well as the top 5% quantile. What we see here is, at least for the point estimator, right, we should talk about inference later on of how to put confidence bands on this. At least for the point estimator, what we see is the non-parametric estimator estimates an asymmetric distribution as well as a much smaller tail than the normal distribution, right? So he thinks that there are not as many bad teachers in the left tail as dictated by the normal assumption. And these did influence how the posterior mean would look like. So here I'm plotting the parametric and non-parametric estimate, the empirical base estimator for the top and bottom 5 teachers that with respect to their outcomes yi. So the non-parametric method is more optimistic about teacher at the bottom, right? So it's tried to shrink more back to 0 versus the parametric ones are kind of giving them a worse outcomes. Top 5%, not so much difference. That's just what we see in the LA data. But the takeaway message is really the non-parametric method offers an adaptive approach, right? Whatever distribution you have is trying very hard to learn it from the data and then adapt shrinkage accordingly. Okay, having all this said, I need to tell you how we compute all of these things, right? So for parametric models, we have a variety of methods. One can use maximum likelihood estimator or the sure estimators to estimate these unknown parameters in the prior. How about the G modeling or the F modeling part? So here is an overview on what are the available tools in this, at least for this normal mean model. So we have the F modeling, which is proposed in Brown and Greenstein, 2009, as well as a couple of variety of methods for the G modeling to non-parametrically estimate G. We have, first I will define the non-parametric MLE, right? So we need to define it. So what is our target? This is done in the early paper by Kiefer and Wolfowitz, who actually proved consistency of this non-parametric MLE. We have the well-known and popular method, EM algorithm, which was introduced into the econ literature by Heckman and Singer in 1984, who really have this non-parametric MLE perspective in their paper. We also have the modern approach, which is the interior point algorithms proposed by Conker and Mizera, 2014, and that is behind the RE-based package. That's the machinery that we use in that package in estimating non-parametric MLE. There is also the Efference log-spline method, which is the machinery underlying this deconvolve R package. So then I'll give some demonstration, and then I will make cautionary remarks on what if G is not point identified, right? So what should we do in that case? Okay, so just very, very briefly on F modeling, since we have the Tweedy formula, which suggests that the posterior mean really depends on the prior G only through the marginal density F, right? Because G is kind of hidden in this marginal density F, and F is the only thing that chips into the base rule. So that leads to Brown and Greenstein suggesting kernel method to estimate F and F prime. Now, the disadvantage of the F modeling is that kernel method usually does not respect the hierarchical structure of the model. Kernel method will not respect the fact that the marginal density F comes out from a mixture model. As a consequence, the resulting estimator using the F modeling in the Tweedy formula is not going to respect the fact that the base rule is supposed to be monotone in Y. It's easy to show that the first derivative of the posterior mean have to be strictly positive. So using F method, you're not gonna have that built-in monotonicity in there. And then a natural improvement, which is suggested in Conker-Mizera, is to impose shape constraints to enforce this monotonicity. However, if we have G modeling, which will automatically respect all these features, why don't we use that, right? So let's first define what is the non-parametric MLE. So the non-parametric MLE, denoted as Gn hat here, is nothing but the maximum probability measure that will maximize the log likelihood, right? So here in the bracket, I have the marginal density sitting there. So that's a usual definition of the maximum likelihood estimator, except that we have an infinite dimensional objects here. So first, for the normal mean model, G is identified. Otherwise, we need to worry about that first, right? That's just the argument in Gaussian deconvolution where the distribution of alpha is identified. So Kiefer and Wolfowitz prove consistency. Lynde, 1985, further characterized the feature of the non-parametric MLE. So he showed that the solution exists and is unique, I think, at least for the normal mean model, and it's going to be a discrete probability measure, means a probability measure that has mass point, okay? And he also showed that the number of mass points gonna be upper bounded by n, and where the mass points are gonna be bounded in the interval of the data, the minimum of y and the maximum of y. There are further strengthening of these number of mass point results. Polanski and Wu show that if the true G is sub-Gaussian, then the number of mass point gonna be of log n. So you will see a lot less mass point, and that's actually what we experience in usual application. Okay, so and just to remark that this method or this definition of the non-parametric MLE is amenable to be generalized to any base density that you would be plugging in again, right? So in the package, we implement Poisson, gamma, and so on and so forth. As long as it belongs to an exponential family, Lindsay's result on characterizing the non-parametric MLE would hold. Okay, so let's first talk about a well-known algorithms to implement this, which is also the algorithm proposed by to be used in Heckman and Singer for their Weibull mixtures in modeling the duration. So how we go about it is we first pick a K, which tells the EM algorithms that I'm going to consider distribution with K mass point. Then the algorithm gonna iteratively optimize the location and the weights put on this mass point. Then we're gonna slowly increase K, right? Because I don't know how many mass points I should have. I'm gonna slowly increase K until the likelihood no longer improves, and I'm gonna settle down at that estimator to be called my non-parametric MLE. Now, this is a tough problem. Anyone who has tried this would know that this is not easy to do. And the underlying reason of it is because this is not a convex problem, right? Because the set of discrete distribution with K mass point is not a convex set. If you do a convex combination of distribution with 2 mass point, you might end up with a 3 mass point, 4 mass point, and so on and so forth. So this is not a convex set. So the problem is not convex. So you face all the trouble of local optima and all that. Then you have to randomly start in different places and so on and so forth. Now, a key observation is relaxing the finite mixture problem, which is inherently built into the EM algorithm, to an infinite mixture problem actually restores convexity, right? Because the whole collection of probability measure is indeed a convex set. Okay, so it pays off to look at the dual problem, which is usually a bit faster to compute. So the dual problem of the non-parametric MLE, you have to take my words for it, takes this form. It has n variables, right, V1 to Vn, but the trouble is it has infinite number of constraints because the dual constraints has to hold for all values of alpha. Okay? Now, the trick used in Konkan-Mizrahi 2014 is to suggest that we can take a fixed and a refined grid for the support of alpha and enforce dual constraints only on the grid. Pretty much how you would bring an infinite dimensional problem to the computer, right? You take a grid. And then basically these will give an approximation of the non-parametric MLE, right? So here we're optimized within this probability measure on the fixed grid. And this turns out to be, again, a convex optimization problem. Since it's convex, you're going to get a unique solutions, and you don't need to random start from different places and all that. And modern interior point algorithms scales very well with sample size n, and is very efficient. And that's what we use in the RE-based package. And under the hook is basically the MoSEC machinery. And this generalizes to a variety of base density. In the package, we include different things. Okay, what about Efference method? So the idea of Efference is we again take a grid. Okay, so take a U1 to UL as your grid for the vector of alpha, for the alpha. Let's assume that G has some smoothness. Let's assume that G has a density, little g, that belongs to the exponential family characterized by a finite vector mu. The dimension of mu is p, right? So, and then we can rewrite the log of the density g would take this parameterized form, where the matrix Q is of dimension L, which is the size of the grid, multiplied by p, which is the parameter that characterizes this exponential family distribution. The else entry of the g is going to be nothing but the density g evaluated at the else grid point. Efference suggested using natural spline to configure the matrix Q. Okay, and so here there are a couple of user choices that needs to be made in using Efference approach. The first is how many mu do we have? How do we parameterize this? So the dimension of mu is a user choice. larger p means more flexibility in this class of density function we consider. And then when we optimize for the vector mu, Efference suggested a penalized likelihood approach, right? So here in the first term, we have the usual likelihood sum up. And in the second term is a penalty terms. It's kind of like a square root of ridge penalty, where in front of it is another tuning parameter. Lambda controls how much shrinkage we have, right? So larger lambda would shrink the vector mu towards the origin, hence penalize the resulting distribution towards the uniform distribution. Let's see how it works in practice, right? So very quickly on two examples. First is we have a discrete G, two mass points, one at 1, the other at 4, with equal probability. On the left-hand side is what's produced by non-parametric MLE, almost spot on for these two mass points. And the right-hand side is the implied marginal density in comparison to the truth. So the blue is the true density, while as the black is the implied non-parametric estimator. So they are, again, spot on. So this discrete G environment is really favoring this non-parametric MLE because it's discrete by nature, right, for the, by Lindsay's result. Now, Efference's approach, by construction, has some smoothness built in, right, because he's targeting the density. So here, I'm picking two types of tuning. So P equals to 5 or 10 corresponds to different level of degrees of freedom, and lambda is fixed at the same quantity. And we can see that the red one is really trying to mimic this two mass point context, and the right-hand side, you can see the corresponding implied density. Let's consider a continuous G, right? And we can see that, okay, NPMLE does produce this almost Gaussian quadrature looking like mass points, these 4 mass points here, with a little bit of smoothing implied, just a kernel smoothed on this non-parametric MLE leads to the red curve here, right? So a little bit of smoothing, you're gonna recover something that is reasonably close to the truth. Of course, that's again a tuning, right? How much bandwidth and all that. And on the right-hand side, we have the implied marginal density. What's revealing is that even though the black is very discrete, the G is very discrete, once you go to the marginal density, it's extremely smooth and actually tracks the truth very, very well. So the mixture model really provides the smoothing that is doing the job of getting you a good estimator for the marginal density. Then this would be the corresponding Efference estimates, which of course works a lot better here, although we again have to choose the tuning parameters. Okay, so just very quickly on a remark on what if G is not point identified, right? This often occurs when the outcome variables is discrete. For instance, consider the binomial mixture, where the yi is binomial with k number of trials and success probability pi. This arises as an application in the Klein and Walters 2021 paper, where the yi's are number of job recalls. So in this model, all we can learn about G is its first k moments, right? So even if I tell you the population frequency of Y, we can only learn the k moments of G. Just knowing the k moments of G, not gonna point identify G. We're gonna have a collection of G that are observationally equivalent. And if our parameter of interest is a functional of G, like in their applications, the posterior mean of P, given yi, for instance, then it's only going to be partially identified, and we are supposed to construct a bound on that. So that's more advanced on how to leverage these non-parametric techniques to kind of come up with a bound. Okay, so in summary, we recommend using empirical-based estimator when collective performance matters, not individual performance, right? So for each individual estimators, they are biased, but as a whole, they produce good performance in terms of mean squared error. And also, we have tools to estimate Gn non-parametrically, and it can be beneficial, especially when n is moderately large. And just a quick slides on probably some of us would have the notion on deconvolution being hard, right? So deconvolution usually have slow rates. In fact, in the normal mean model, the rates is logarithmic. So it is hard problems. The reason is because even if for two different G1, G2 very different, their corresponding marginal density could be very similar. So you have a hard time distinguishing using the data which G it is. So that's why you need extremely large N in order to kind of have the convergence, right? Okay, but oftentimes what we are interested is not the G itself. It's some functional of G, right? So if the parameter of interest results from smoothing Gn, then performance can be good. For instance, the marginal density is smoothing Gn, and we indeed have encouraging Hellinger risk bound documented in a sequence of theoretical papers. And in general, for linear functionals, I would defer the reader to Vandergeers. She has a chapter on discussing what are the assumptions that leads to good properties of linear functionals of this non-parametric MLE estimator. Okay, and also learning this distribution G opens doors to other inquiries about the parameter alpha. For instance, we might be caring about heterogeneity, which is measured as the variance of alpha. We might be caring about tail probability, which again is a functional of G. The tail mean can be written as a functional of G as well. And also, learning G opens the door to consider other compound decision problems where this G is going to, again, show up and as an underlying machinery to construct a non-parametric method. So now let me bring you through another simple example on compound decisions. This is really the Robbins 1951 paper. So again, almost a normal mean model, except now we specialize the alpha I to just take two possible values, -1 and 1. Before, it's situated on the real line. Now we only have two values. In this context, maybe an absolute error loss is more natural because our decision going to be -1 and 1, the true parameter going to be -1 and 1. Designing in this way, we're going to incur loss 1 if delta I makes around estimates, otherwise 0. So again, the compound risk going to be the expectation of the aggregated loss. And here, the non-parametric distribution of the vector alpha can be characterized by just one number, which is the empirical frequency of how many ones we have in this vector of length n. Okay, so again, consider compound risk for separable estimator. We again have the fundamental theorem of compound decision arise, where we connect the compound risk to the base risk, where we have a prior Pn showing up here, where Pn summarizes how many ones we have in the vector of alpha. So then going through the same idea of we have the base risk, let's work out what's the base rule. And with that loss function, the optimal base estimator for any Pn gonna take this form. And this form suggests that if your true Pn, right, what you kind of don't know as oracle knowledge, is larger than a half, then you basically put a factor that shrink, quote unquote, upwards, right? So you inflate y if the Pn is greater than a half, and otherwise it becomes a negative quantity, so you shrink it downwards. So again, it has this shrinkage flavor built into this base rule. Not knowing Pn, Robbins go ahead and suggest why don't we estimate it from the data, right? A natural method of moments estimator would just be counting how many, basically this can be easily seen as the method of moments estimator for how many ones we have in our data. And Hannon and Robbins 1955 further proved that as long as we have a consistent estimator for Pn, as n goes to infinity, again, the regret would vanish, right? So this is the minimal risk benchmark, while as the left-hand side is the risk of using the estimated non-parametric estimator. So we see that when Pn, if the truth is a half, then the optimal base estimator corresponds to the MLE. So the maximum likelihood estimator would just tell you estimate 1 if sine of y is positive, estimate -1 if y is negative. Okay, now, so in that context, using the base rule, we can show that it's just at most epsilon worse off, and this epsilon is small p1. But for any other value of Pn, we're gonna be much better off using Robbins estimator than sticking to the maximum likelihood estimator, which has constant risk. And this is being plotted in this figure here, where on the left-hand side, I have sample size 20. The red curve here corresponds to the mean absolute loss for the maximum likelihood estimator, so just the sine of y. The black curve here is the Robbins estimator, where we try to estimate Pn and mimics the Bayes rule. Where the green one is the oracle, where we know the truth of Pn. So we see that with n equals to 20, we have a battery of p-values where we are already much better off than the maximum likelihood estimator. On the right-hand side, one sample size increased to 100, then even at the least favorable case where p is a half, we're really mimicking the oracle rules. We're not too much worse off compared to the maximum likelihood estimator, but much better in other values of p. And how does that simple Robbins compound decision problems connects to multiple testing? Right? If I bring you back to the normal mean problem where alpha I is again on the real line following some distribution g, where our interest is no longer the vector of alpha, but we are interested to know which alpha I doesn't belong to a set of value A. Okay? And if we set this A set to just contain the 0 value, we are testing for significance. Right? We want to know who has the alpha i's not equals to 0. That's just a testing context. So here, a key observation is that we transform our parameter of interest from alpha I to this binary parameter, which is denoted as hi here, which just tells me whether you are indeed in the set A or not. Right? So then focusing on this, the compound decision with the following laws, which characterize how much loss you occur if you commit a type 1 error or a type 2 error. So they are weighted by 1 minus tau and tau. Then the Robbins context starts to kick in, right? We again have binary parameters. We want to come up with estimators that minimize the compound risk. So here, the distribution of the new parameter of interest is again characterized by one number, P0 here, which is just the probability of hi taking value 1, which links back to the g on g evaluated on the complement set of A. So the optimal Bayes estimator gonna take this form. So it's gonna truncate, right? So we have a tau truncation on the posterior probability of alpha I belongs to the set A, given the data evidence yi, where the posterior probability is nothing but a function of g, right? So that leads us back to g. If we learn g, we would know how to come up with this posterior probability, and then we're gonna use that to rank individuals and do a thresholding rule to decide who are to be rejected and who are to be not rejected. Okay, so then the choice of tau, right? We still have that degrees of freedom. The choice of tau gonna lead to different false discovery rate, which is the proportion of false rejection out of all rejections. So by tuning the tau, you're gonna have different targets of FDR. How does that connect to ranking and selection? So in this paper with Roger, we consider the empirical Bayes method on ranking and selection. So think about the teacher context. Suppose that now we want to estimate the top Q% performers. Right? We want to know who are the teachers that has their latent value added in the top Q%. The parameter of interest then convert from alpha I to this binary hi, just like before. And then we're gonna rank teacher by the local false discovery rate, which is nothing but this posterior probability or the posterior tail probability, right? Looking at conditional on the data evidence yi, what is the posterior probability of the teacher I having a quality below certain quantile. And we're gonna threshold by, given a tau, we're gonna threshold who are the teachers that we say are in the top Q percentile. So the first, a remark on the measure we use to rank teacher. So if we are in the homogeneous variance context, imagine all your teachers teach the same number of students, then all their variance are the same. Then ranking with the MLE estimator is going to be equivalent to ranking with any monotone transformation on that, because ranking is just ordinal information. And we probably have already seen that all these parametric, non-parametric EB, or local false discovery rate is all gonna give you the same ranking because they are all monotone transformation on the MLE, which is yi. However, if the variance is different across individuals, then different EB methods can produce different rankings. So we documented these in that paper. Second remark on the role of tau. So here, tau could play two roles, right? Tau controls the false discovery rate, the proportion of false rejection out of all rejection. Tau also controls what's the proportion of selection we make, how many teachers we gonna say belongs to the top Q quantile. So what we did in that paper is to basically design a loss function to achieve two goals. One is what we call capacity constraints, because we do only want to select Q%. And second is FDR constraints, because we want to avoid making too many false discoveries among the teachers that we have selected. So then leads to a data-driven way of selecting the tau, and then everything holds up together as a ranking and selection approach. Okay, so very, very briefly on empirical-based inference. This is, as I mentioned in the beginning, quite underdeveloped. So if we look at the normal mean model, and if we specialize to the normal prior, which is done in the Efference and Morris context, then the Bayes estimator are going to take this simple form, which we've seen before. We can work out the Bayesian credible set for alpha I with 95% coverage, right? So the posterior mean is going to again follow normal. Then the 2.5 quantile and 97.5 quantile are going to give you the Bayesian credible set for alpha I if we know everything about the prior, right? If we know the parameter A in that prior normal, then we can use the Bayesian credible sets as a confidence interval for alpha I. Now, the EB context is going to say, I don't know A, I'm going to estimate that, right? So it's going to have a naive EB confidence interval, which is just plugging in, replace the A by the estimator A hat. But that does not account for the fact that you have estimated A, right? So these could give poor coverage when n is small, and Morris in 1983 provides a finite sample correction, meaning that we add an additional correction terms to account for the fact that we have estimated A. Now, if the prior is not normal, then in the recent paper by Tim Armstrong and co-authors provides a robustified EB confidence interval, right? So the idea is the usual naive EBCI gonna have poor coverage if we deviate from the normal prior. Then the idea is to come up with a different cutoff value, the critical value C tau hat here, chosen in such a way that we have average coverage, right? So the average probability of alpha I in the confidence sets is guaranteed to be greater than or equal to 1 minus tau. Now, this is great because for people that were using the parametric EB method, this is a very natural idea because the confidence interval is centered at that linear shrinkage estimator and gonna be symmetric around that. And they would guarantee, at least in using that criteria of coverage. However, let me try to end my talk with a compound decision, right? So an alternative way of viewing the confidence interval construction is a proposal in this comment in Jiaying 2021, which is to really kind of write it down as a compound decision problem, right? So all we want to do is to come up with confidence interval. Here, the left end gonna be A applied on the individual coordinate yi, and right end gonna be B, a function B applied on yi. What we want to do is we want to minimize the average widths of the confidence interval subject to the same coverage criteria that is proposed in the Armstrong paper, right? So given these, we could write down we can design a corresponding loss function that would allow one to find the function A and B, which will give you a non-parametric way of constructing confidence interval, which again had that coverage property. Okay, so with all that said, let me conclude by saying that empirical-based method can be useful for economics applications. I just gave one. Chris gonna give more applications. And as we become more interested in modeling unobserved heterogeneity in different contexts. Herbert Robbins, who is my hero, of course, is way ahead of his time in proposing the non-parametric empirical-based method in the 50s. Now, with the availability of large-scale individualized data sets becoming increasingly available, and modern computational methods facilitates the estimation perspective, really hopefully made it feasible to apply his method. And of course, this is still an ongoing research area that a lot can be done, especially on the ground on non-parametric methods, that hopefully this lecture would inspire some interest. So thank you very much. That's it.